Today, the main theme of your experiment will be the periodic table. This is a compilation of the elements put together about 125 years ago independently by Dmitry Mendeleev, a Russian, and Lothar Meyer, a German. They originally arrived at this arrangement by placing the elements according to chemical and physical properties. Thus, all the elements in a vertical column, these are called groups. For example, this group or this group, all the elements in a single group tend to have similar chemical property. Also, as you go across the periodic table in something called the period, the relative change in physical properties as you go across this period tend to repeat itself in the subsequent periods. Although the periodic table was originally designed by observation of chemical and physical properties of the elements, modern atomic theory has confirmed this arrangement. Thus, the elements are arranged in order of increasing atomic number, and also elements in a group have the same valence shell electron configuration. This then accounts for much of the similarity in the chemistry of the elements in a group. So, if we're looking at the periodic table, we can see that the atomic numbers increase as we go across the periodic table and as we go down the periodic table. Also, if we look at any one of the groups, they will all have the same outermost electron configuration. That is the valence shell electron configuration. In the valence shell, then, all group 1a elements have one electron in an s orbital. Similarly, any group 6b element will have 2 electrons in the outermost s orbital and 4 electrons in the outermost p orbital. Up until now, we've emphasized the similarities of the elements within a group, but perhaps more important is the ability to use the periodic table to predict some of the differences which may occur within a group. Today's experiment will emphasize 2 trends which exist within a group. Now, there are occasional exceptions, of course, but as you go down a group in the periodic table, everything else remaining the same, the size will increase. What that means is an atom or ion at the bottom of a group will be larger than an atom or a corresponding ion at the top of the group. The second trend involves removal of electrons. In an isolated atom or ion, that is an atom or ion in the gas phase, it is easier to remove an electron from something at the bottom of the periodic table than from the top. What we're saying is that it is easier to remove an n equals 5 valence electron than an n equals 3 valence electron. Applying these ideas specifically to today's experiment, we'll study the solubility of group 2 cations with various large anions. Now, this will depend mainly on the size of the group 2 cation. We will also study the oxidation of the group 7 halide ions. Now, while this is a more complicated case, it will depend in a large part on the ease of removal of electron from the halide anions. Looking first at the group 2 elements, they include beryllium, magnesium, calcium, strontium, barium, and radium. Radium is not included here because it only exists as radioactive isotopes. Also, today you will not be studying beryllium because most beryllium compounds are very toxic. So today you'll be dealing with magnesium, calcium, strontium, and barium. All of these group 2 elements have the s2 valence shell electron configuration. These 2 electrons are very easily lost to give the +2 cation. Group 2 elements are electropositive, and with the exception of beryllium, their hydroxides then are alkaline. Magnesium and calcium are particularly common in the Earth's crust, and they form minerals such as dolomite, feldspars, and of course limestone. Now, because of these last 2, the elements in group 2 are frequently referred to as the alkaline earths. Now, these are some of the similarity. Now, let's look at one of the differences. While all the group 2 elements form +2 cations, the size of these ions varies, increasing as you go down the group until the diameter of the barium ion is more than twice that of the magnesium ion. You'll allow each of the 4 group 2 cations to react with 4 different anions. That's 16 possible reactions in all. The anions you're going to use are the carbonate ion, the sulfate ion, the oxalate ion, and the chromate ion. 2 things about these anions. First, they all have the -2 charge. So when they react with group 2 cations, they'll react in a 1-to-1 cation to anion stoichiometry. That's given in this generic equation down here. Now the other thing about these anions is that they're all fairly large in size. Now what is the importance of that? Well, there's a fairly reliable solubility rule for ionic compounds in aqueous solution. If both the cation and the anion are large, or if both are small, the compound generally tends to be insoluble. On the other hand, if one is large and the other is small, the compound tends to be soluble. Well, let's see how all this works in today's experiment. This is a sample of what you'll be doing today. There are 4 tubes here, and each of them has the carbonate ion in them. To the first, we'll add barium ion. To the second, we'll add calcium ion. To the third, we'll add magnesium ion. And to the last, we'll add strontium ion. Now we're adding about equal amounts of each. Now what we'll do is we'll stir these up. Make sure you clean the stir between each of these tubes. And now we're ready to make and record our observations. In recording observations, if you mix 2 solutions together, there are at least 2 things you should note. First, you must note the phase or phases which are present after mixing. If a solid forms, it's a precipitate. If no solid forms, call it a solution. If you see gas bubbling out of the solution, that's effervescence. Now, the other obvious observation is color. Please do not assume that the color is obvious. If a white solid forms, call it a white precipitate. If nothing appears to happen and the resulting solution is clear and colorless, call it a colorless solution. Today, your most important observation will be whether or not a precipitate forms. But if a precipitate does form, you should try to describe it correctly. Most important is color. This is always important. Next is the amount. This, of course, can depend on how much of each solution you use and the concentrations. But you should note the amount as either a little or a lot. And sometimes in analogy with rain, the terms light and heavy are used. A heavy precipitate means a lot of precipitate. Finally, you should describe the individual particle in the precipitate. Now, this again can vary depending on how the precipitate was carried out, so it's not as absolute as color, but there is a standard vocabulary that you use here. If, when you look at a precipitate, the particles are too small to see, they're called colloidal. A colloidal precipitate has a milky look. If you can see the particles, but they're small, the precipitate is called finely divided. That's like sand. But if the particles are bigger and look like big snowflakes or feathers floating around, the precipitate is called flocculent. If the precipitate has bigger particles that look translucent and sticky, not feathery, but gloppy, it's called gelatinous. For example, in making Jell-O, you start out with a finely divided solid, but when you add the water, the particles start to swell and become gelatinous. Finally, the particles are big and chunky, like in cream cottage cheese. Such a precipitate is called curding. Now, a word of caution. The precipitate's texture can change with time. It's not uncommon then for a precipitate which starts out as colloidal to change over a period of time to finely divided or even curdy. Back to our experiment, and let's make our observations. We won't worry too much about texture today because it isn't important here. Now, the barium carbonate, I'd say that's a lot of white, finely divided precipitate. Calcium carbonate, about a medium amount of white flocculent precipitate. The magnesium carbonate, very little white flocculent precipitate. And the strontium carbonate, well, that's a lot. It's white and it's finely divided to flocculent precipitate. Here's a close-up of the magnesium carbonate precipitate, and as you can see at this point it has a feathery-like look, so this would tend to be flocculent. On the other hand, the barium carbonate appears to be more finely divided. In any case, the important thing here though is that a precipitate is or is not formed. Now we'll turn our attention to the group 7b elements. These include fluorine, chlorine, bromine, iodine, and astatine. Now, astatine only exists as radioactive isotope, so we won't include it here. We'll also not study fluorine today because it's a very reactive gas. This reactivity makes it very hazardous to handle. The halogens react with metals to form salts, hence their name halogens, which means salt formers. All of these elements have the s2p5 electron configuration in their valence shell. That's 7 electrons in the outermost orbitals. To complete the octet, the elements exist as a dimer, where they share an electron by forming a single bond. They can also pick up an electron to form the -1 anion. These are the so-called halides. Now, this tendency of the halogens to pick up an electron makes them very good oxidizing agents. Before we go on, a cautionary note. The halogens can be hazardous. Do not breathe them or spill them on your skin. And also, don't confuse the halides and the halogens. Table salt is sodium chloride. It contains the chloride ion, which is a halide. On the other hand, chlorine is a halogen. It was used as a poison gas in World War I. In today's experiment, you'll study the halogens. That's chlorine, bromine, and iodine. In particular, you'll look at their oxidizing powers. Now, in this process, you'll also measure the ease of oxidation of the chloride, bromide, and iodide ions. Before we go on, recall that oxidation involves the loss of electrons. That is, something which is oxidized loses electrons. The halide ions are what you're going to be oxidizing today. Now, here's a simplistic drawing of their electron shells. Now remember, in the gas phase, it is easier to remove a valence electron from the n=5 orbital than from the n=3 orbital. The reason for this is that the negative electron is attracted by the positive nucleus. In the n=5 orbital, it is further away from the nucleus and therefore less strongly attracted.